So last time we started talking about exponential families, and we discussed the basic definition, which is a family of distributions dominated by some measure nu, let's say, and then given these, or because the family is dominated, we'll have density. So each probability distribution here has a density, and that density has this exponential form. And the form that's written, the density is written in, immediately gives you that this T of X is sufficient. This is the parameterization that maps some sort of potentially abstract parameter space into RD. So these, both of them are RD dimensional, and so you can define inner product and things make sense. This is the log partition function, which automatically comes out once you specify the eta, t, h, and nu by the fact that the density has to be normalized to be a probability density function. So from the normalization sort of constraint, we can determine A, and the set of parameters for which this A is finite is actually what we have a valid density for. And so this is the parameter space that you're actually going to work with. So we saw a couple of examples. There are a lot more. And then we discussed this idea of regularity conditions. One of them is about the parameterization. So that omega naught, if you recall, that's the what I called actual parameter space, the set of thetas for which A theta is finite. So eta omega is just the image of that set under eta transformation. So the set of all eta thetas that you get where theta is in omega naught. So this would be a subset of RD, right? And the idea here is that we assume that this subset of RD has non-empty interior. So did you guys get a chance to recall or review what an interior is? So what do we mean by a non-empty interior? Anyone? Union of all open sets of a set. So this is close enough, but it's not quite. So what do you mean by all open sets of a set? So what is an open set of a set? That's a little bit vague. Do you want to maybe elaborate on that a little bit?
An open subset, I just remember you can draw like a circle around it and you're still in the set.
Okay, so maybe you want to rephrase that as a union of all open subsets that are inside a set, right? So if I have a set open, so suppose I have a set, I don't know what we should call this. Let's say this is S. So I take the union over all sets O, such that O is a subset of S and O is open. Okay, all the open sets that are inside a set. So you can say that this is the interior of S. In a sense, it's so another way of saying it's the largest open set that is inside S, or a subset of. So the largest open set that's inside the set, the closure you can define similarly. It's the smallest closed set that contains the set. So you have a set the largest open from the inside and the smallest closed from the outside. Those are the closures and the interior. There's another easy way, like in metric space. So this is like the topological sort of, from a topology definition, it makes sense and it's very general. It's a good definition, okay? But what is, like if we are in a metric space, there is a simpler characterization. So the interior, basically the points that are in the interior are called interior points. So how can I identify an interior point of a set? What point is in the interior? Any point that's not in the boundary. Yeah. So then the question is, what is the boundary? That's sort of that's true, but it's not like it's any point that's in the set and it's not on the boundary of the set. Closure minus the interior. Yeah. So, but you're using the definition of the interior here. So, can we get like give another? So.
If you have a metric space and you have a point on the boundary, any epsilon ball that you draw around the point on the boundary will include points both inside the interior and the exterior.
Okay, very close. Yeah. So another way of rephrasing it, so instead of doing it in terms of the boundary, just you can say that the point is in the interior if whenever I, or not whenever, there exists like a ball, an open ball, with a radius sufficiently small that's entirely contained in the set. Things that are on the boundary, you can't do it. Things that are outside, obviously, you can do it. But if it's in the interior, you can put a ball of small radius such that the ball is entirely in the set. That's like the intuitive idea. So suppose you have you're on the real line. If you're looking at the closed interval 0 to 1, because the balls here are just intervals, open intervals, anything that's like not 0 or 1 is in the interior. So the interior of 0, 1, let's say as a subset of R, in R, is the open interval 0, 1. Because when I put a ball here, which is an like a open interval, I can make it interval small enough such that for any point that's between 0 and 1, such that it's entirely in the set. The interior of this guy, if you view it as a subset of R2, if I view this interval as a subset of R2, what would the interior be? Something like this. So think of this as a subset of R2. What is the interior of this guy? This is like -1 to 1, let's say. Suppose, or yeah, let's say this is unidimensional, this is multidimensional. Yeah, so the interior, this is not like empty because any point here, if I put a ball, open ball, no matter how small I make the radius, some of it is outside. So this has empty interior in R2. So we want to prevent this. And you can imagine any set basically that sort of lacks a full dimensional piece. So let's say curve in R2. This is going to have an empty interior. Okay. If I add a little bit of substance here, this union with this, then this is fine. So there are points, the interior is not empty. So this is a really mild condition. So it prevents things that are sort of, in a sense, lower dimensional subsets of the RD. Okay. And then the other condition we discussed last time. So this is saying that there's no affine combination or linear combination of the components of t and 1 such that I can get it like identically equal to 0 almost everywhere for some coefficients that are not all 0. So this is like a sort of linear independence assumption, linear independence in the sense of linear algebra. So these are linearly independent, almost surely. So we're going to make these two assumptions, and we call the family full rank. Okay, and I mentioned that this E2 is related to identifiability. So if it fails, so here's an example where it fails. So you can model the Bernoulli family as a 2-parameter exponential family with a sufficient statistic that has these two coordinates, x and 1 minus x. And you can see that the two coordinates, they sum to 1, so they satisfy this affine constraint. And so this family is not full rank. And you can imagine that these two have to satisfy a constraint as well. So the Bernoulli family can be parameterized by a single parameter. So you're over parameterizing. So some of these values of theta naught and theta 1 give you the same distribution. So the model is not identifiable. This is a case where the second condition is fails. So that's again. So the image of omega in this case R would be like a parabola in R2, and so this would be image of omega. And so this fails that condition. So these things are sometimes called curved exponential families, related to this idea, which there's a bit of discussion of that in your book, but we are going to mainly focus on things that are not curved exponential families. Okay. Questions, comments? Okay, so the main result is that in a full rank exponential family, a family that satisfies those two conditions, T is complete. The sufficient statistic is a complete statistic. So that's the result that we actually appealed to multiple times in the past, and you can use it in your problem as well. So the completeness proof follows from Laplace transform arguments. Basically, you have to show that the Laplace transform is invertible. And I'm not going to do it. I'm just going to prove that it's minimal sufficient. So let's accept the completeness. We're going to prove minimality, which is simpler. And in order to do that, we are going to use the idea that we can first show that T is sufficient. So we know that by factorization theorem, that's easy. Then pick a subfamily and then show that it's minimal for that subfamily, minimal sufficient. And then you're done by that lemma. So the idea here is that because, so remember eta omega is open. It's not open, but it has non-empty interior. So I can pick let's say this is open, like this is not open. So interior of omega is non-empty. Okay, so it means that there exists like a theta such that eta theta is in the interior of omega. Sorry, is in the interior of eta omega, right? And I'm going to call this eta actually. So this value of theta, I'm going to call it eta for simplicity. So eta of that particular theta, I'm going to call okay, sorry. yeah, let's do, this is going to be, let's say eta 0. I'm going to do it, I'm going to call it eta theta 0. So I'm going to call it eta naught or 0. Okay, so there exists something like that. So this is omega naught, and this is mapped to RD, to some other set. So I'm picking theta naught here. This is mapped to eta naught somewhere. And the idea is that because eta naught is in the interior, I can choose something that's in the interior. I can put a small ball around it, and it's entirely inside the set. And then because it's a full dimensional ball, so I can put like a coordinate axis completely inside this. So I can go in every direction without, if I move a small step in every direction along the coordinate axis, I'm still in the set. So basically I can find like eta 1, eta 2, eta 3, and jump to eta d, such that the difference, so eta 1 minus eta naught, eta 1 minus, so eta 2 minus eta naught, eta 3 minus eta naught in this case, and in general up to eta d minus eta naught, these vectors are linearly independent. So let's say do it as set eta 1 minus eta naught, eta 2 minus eta naught, and eta 3 minus eta naught. These are independent, linearly independent vectors because they're sort of in the direction of the coordinate axis. Is this clear? Sort of. The non-emptiness of the interior here is key. So. Okay, so I have that. And so if I form a matrix whose, so consider A transpose whose columns are these. These are, I'm going to put these in the columns of A transpose. So this would be a full rank matrix, D by D full rank matrix. And if you recall, we'll have P theta I of X is X eta theta, which is going to be eta I, the way I define it. So eta I is just eta of theta I. And then T of X minus eta theta, and then theta I, and then h of X. So if I form the likelihood ratio relative to theta naught, this would give me X eta I minus eta naught, T of X, and then minus eta theta I plus eta theta naught, and then h of X goes away. So that's the likelihood ratio. And then if I put these together, if I put them in a vector, it's not hard to see that I'm going to collecting, I'm basically collecting yeah, so let's say take the log. So you take the log. Let's do it here. So if I take the log, I'm going to remove this X here. And then when I put them together, these are some constants. So the log P theta 1 X over P theta naught, dot log P theta D X over P theta naught X. This is going to be equal to eta 1 minus eta naught Tx dot eta D minus eta naught Tx. And then plus these constants, which I'm going to ignore. So this is constant. So you care about the log likelihood up to a constant shift. And this you can write as, this is like each one is, so this one, for example, is eta minus eta naught transpose T of X. So, and these are like, A transpose is like that, eta 1 minus eta naught transpose and eta 2 minus eta naught transpose, the way we define it. So this whole thing can be written as A times T of X. Okay, and then plus some constant, which I'm going to call it B. Okay, does that make sense? So it's just some algebra. And so what you get is, this is plus some constant. So A times T plus some constant. We know that this is going to be minimal sufficient for this subfamily, the subfamily parameterized by theta naught up to theta D, because this is the, it has common support, the family has common support, and we know that the likelihood ratio vector basically is minimal sufficient. So this is minimal sufficient. A is invertible, and so this guy is in one-to-one correspondence with T, basically. It's in bijection. So invertibility of A follows from the fact that we managed to construct these this linear, like set of linear independent vectors, which follows from the non-emptiness of the interior assumption. So A is invertible, so T is in one-to-one correspondence with the minimal sufficient statistic. So T is minimal sufficient for P naught, the subfamily, and so T is going to be minimal for P as well. Sounds good. I guess last year someone asked whether we used the E2 here, and I believe we didn't. So it seems like this result holds, even if your parameter is not identifiable. So if T has fails to satisfy E2, you just have that the interior of the parameter space is open, then you're good. Whether T being complete requires it, it's a good question. So I don't remember it from the top of my head, but you're welcome to dig into the literature, see whether it's needed. But definitely if it's full rank, then all is good. Questions? Comments? Okay, so this is the first major result about exponential families. So we're going to see a couple more of these. This simplifies a lot. Okay, so we have a question. Oh, can you please clarify again why they have the same support? Anyone can tell us why they have the same support? Let's go back to the definition. So an exponential family has that property that the densities have common support, or the distribution has common support. Why is that? Yeah, so H basically, H in combination with nu basically determines the support of the distribution, and these two do not depend on theta. So this part that depends on theta is strictly positive, so exponential cannot be 0. So the part that depends on theta doesn't affect the support. So this can be 0 in certain areas. Let's say this is the Lebesgue measure. Then the support is determined by where h of x is 0, essentially. And that doesn't depend on theta. So they all have, I mean, all the densities will have the same support. Is it clear now? Yeah, good. Other questions? So by common support, just to remind you. Okay, so let's move on. So this was the general form of an exponential family. Sometimes it's easier to just work with, so you can reparameterize in terms of this eta. So instead of using the original abstract parameter, you can use this eta, or in other words, you can say that I'm just gonna rename that eta to be theta. So I'm gonna assume that this is theta. So somewhat without loss of generality, you can work with these so-called natural parameters. So an exponential family where this is the parameter is just theta, or if you will, eta. Doesn't matter which way you call it, but the parameter is in RD basically. That's called eta equal theta is called the natural parameter, and the family is in it's called in canonical or natural form. We often work with full rank canonical exponential families. That's sort of standard view. So from now on, usually we assume that this is theta, usually. And so then the parameter space, what I call actual parameter space now is going to be just what's called a natural parameter space. So it's a subset of RD, and it's the natural parameter space, and everything is nice because we're working RD now. So then if that's the case, then let's not call it degree of freedom, but one of our choices, which was just to set like pick eta, is gone. So we are only left with basically T of x, h of x, and the underlying measure. And then if you absorb under the h of x into the nu, so we basically have this nu T of x and basically the choice of the sampler space. So if I, for example, pick x to be r, and take T of x basically this, and then if I take nu to be, take the Lebesgue measure, then basically the family would have this density. It's a two parameter family, and then A is like this and has to be finite. You can easily see that theta 2 has to be negative for this to be finite. And so the natural parameter space would be that. And it turns out that this would just give you the normal family. So if I pick these, so a natural two parameter family whose sufficient statistic contains x and x squared over R would be a Gaussian. If you just pick x, you would get, let's say, the exponential family. If you pick x, x2, and x3, you get a different family. So if you take x and sine x, that would be a different family if at all possible. X and e to the x, let's say, is another family. So with x and x squared, that's the Gaussian family. And you can easily sort of see from this, because the density is quadratic, like exponential of a quadratic. And then you can match these natural parameters to the usual parameters, on nu and sigma squared, by writing the densities. I believe we have done something like this before, but it's easy for you to write it down, and you can also see that theta 2 has to be negative, because it's negative of, I think, 1 over 2 sigma squared. But you just can define an exponential family like this and then determine its properties. Okay. Questions? Okay, so I can extend this, for example, instead of taking, if I have a vector, let's say in RP, nu tilde is the Lebesgue measure. The sufficient statistic I take as all the xi's, and then all the interactions between xi's, and then all the xi's is squared. Okay, so all the basically quadratic functions. So these are simple quadratic, like the building blocks of a quadratic, like a polynomial. If I want to build a quadratic polynomial of x, I can do it by combining these. So I'm gonna take these, and then I'll have a family. So the family would be like a natural exponential family associated to each one of these coordinates of t of x will be a parameter. So I'm going to call these parameters theta I, and then these parameters are going to be 2 theta ij, theta big theta, and then theta ii. So the 2 here is for simplicity, just we can call it theta ij. But we'll have basically p parameters here plus p choose 2 parameters here plus another p parameters there. So the whole thing would be like 2p plus p times p minus 1 over 2. Right. And I believe, yeah, something is not quite right here. It should be probably 2p. So the family is like d-dimensional, where d is this. And okay, so yeah, so I can write down the density like that. So it's just, this is like theta tx, where theta is just, I'm calling the different elements by different names, but that's basically this part. If you multiply basically each one of the coordinates by the theta, corresponding theta, and then sum, you get this expression. And then there's this log partition function, which makes it normalized. And you can compactly write this using some sort of a shorthand notation. So if I define an inner product between symmetric matrices, so this is the notation I'm going to use. The inner product between theta and x transpose, both are symmetric matrices. In general, let's say if I have two symmetric matrices, A and B, I define the inner product as trace of AB. So these are symmetric matrices. In general, it would be AB transpose, but for symmetric matrices, transpose doesn't matter. So if you look at this, the claim is that I can write this expression like that. This part should be, if you're familiar, it should be like x transpose theta x. The way we added the 2 here sort of makes it like that. This should be familiar to people who have worked with quadratic forms. You can just expand. X is just x1 up to xn. So xp, and then theta is a p by p matrix. Theta contains like these elements, and it's in p by p matrix. And so p by p. And then this guy can be written as a trace of x transpose theta x, because it's scalar. So it's the same as a trace, and the trace has this circular property. I can write it like that. So I can move this to the other side. And then this is just this inner product. So, and then this is just the inner product. If you write it this way, you can see it's like just like theta t of x, except that our t of x is basically now is like x and then xx transpose. This part is a matrix. But the whole thing is just the inner product of theta, and then x transpose with the inner product defined like this. It's just a summation of these two terms. So this makes it a little bit more compact. It's just the notational convenience. Okay, so this is a d-dimensional, like 2p plus p times p minus 1 over 2 dimensional exponential family. It turns out to be just a multivariate Gaussian. So if you compare with multivariate Gaussian, the density, you expand and you compare. you can see, for example, that theta, if the multivariate Gaussian has covariance matrix sigma and mean vector mu, then theta would be like this, and capital theta would be negative sigma inverse, just similar to the formulas that we have here, but just the matrix form of it. And from that, you can actually read what this log partition function is, which is, you read it from here, and then you translate it to theta and capital theta. So in terms of theta and capital theta, would be like this, plus possibly some constant. Okay, so the canonical exponential family corresponding to these quadratic terms are like quadratic or linear and quadratic functions of the coordinates is the multivariate Gaussian. Questions? Comments? So I have one last bullet point here, which is just a comment that this natural parameter, this theta, you can see it's related to the inverse of the covariance matrix. This is sometimes called the precision. So the inverse of the covariance matrix is called the precision matrix, and this is scaled multiple of the precision matrix. And it turns out that this has interesting properties. So if you look at this, whenever theta I j is 0, these terms, the interactions are not present. And so when theta I j is sparse, a lot of these interactions don't affect the density. And this is like a general, sort of falls within a general framework of graphical models. So this is an exponential family, at the same time it's a graphical model, in the sense that basically this is just off, again, like the detour, not necessarily needed for this course, but I can represent conditional independent statements in this model by a graph where I put an edge between two of the nodes. So the nodes correspond to the coordinates. So I have, if I have p variables, basically p coordinates, p variables, I have p nodes in this graph. And then I put an edge if theta ij is non-zero. So theta ij is not 0, I put an edge. I don't put an edge if it's 0. So the edges that I have are those for which theta ij is non-zero. Then you can argue that in general, separation in this graph, so if two nodes, for example, first you can show that two nodes are not connected. Basically theta ij is 0 if and only if they're independent conditional on the rest of the variables. So if theta ij is 0, for example, between these two, let's say this is k, this is l, then xk is independent of xl given all the other nodes, all the other variables. That's the meaning of the graph, but then you can also show more that once I have this, then if I pick any subset of nodes, let's say I pick these two, and I observe that if I look at this, if I look at this set and these two sets, so these two nodes, or these these three nodes, I have these three nodes, these three basically in a set, and then I have these two nodes in a set, and I have another subset here. So L and then the other node. So basically this set is going to be independent of the yellow set given, say, given the blue set. Okay. And the reason is that the blue set separates all the paths from the yellow part to the purple part, basically. So once you have this graph, basically, we can construct the graph by the basically location of non-zeros in theta ij. Sorry, basically all the non-zero elements of theta would give you the edges in the graph. And then once you have the graph, you can read these conditional independence statements. So whenever two sets are separated by another set, and separation in the graph, then those two sets are going to be independent given that separating set. So this is, we haven't proven it, but it's a fact of graphical models. So this representation, this canonical parameter representation, is very much related to graphical modeling and conditional independence sort of statements in the model. So it's interesting in its own right. The covariance matrix directly doesn't give you these conditional independence, but the inverse gives you these conditional independence statements. So for this reason, this model is sometimes also called Gaussian Markov random field. So it's a field because sort of it models sort of independence between these coordinates. And its Markovness is these conditional independence, basically some statements. So something is independent of something else given some other thing. This is like a Markov type statement. So these are called Gaussian Markov random fields. Questions, comments? This was just a quick comment. There's like a whole literature subfield of statistics, machine learning, talking about these things. So an example of an undirected, say undirected graphical model. Also directed graphical model, undirected graphical model, which is also an exponential family. So the multivariate Gaussian is many things, including these two things. It's both a graphical model and an exponential family. Questions? All good? Am I still on? Yeah, okay. That's good news. So to see like how interesting these constructions are, I can take this same set of statistics and I can change the underlying space. So instead of R to the P, I can think of a discrete space. So let's say I would have, instead of this, I could think of a discrete cube. So that would definitely not be a normal distribution anymore, but I can define an exponential family there. So take x to the 0, 1 to the p. Nu tilde would be the counting measure on the cube, but I'm going to use the same statistics. So if I have the 0, 1, then I don't need to include these guys because like if it's 0, 1, xi and xi squared are the same. So I'm going to just pick the xi's and the pairwise interactions. And I can also like do it for a general set of graphs. So instead of including all, I could include them for any fixed set of edges. It could be everything, but I could also have the edges. This is like here where you could have just assumed that some of these theta ij's are 0. Basically, if you assume that they're 0, it's equivalent to just include xij's for ij's that are in an edge set. So if I do that, what I would get is this model. So okay, not 0, 1. Let's say I'm doing -1 and 1, but it's the same. And so x is, so suppose you're given a graph V and then the edge set is E, you can for simplicity take V to the 1 to N, or could be P to be like consistent with the previous example. E would be a subset of the Cartesian product of V itself, basically. This could be like 1 to, usually not except like the diagonal. So 1, 3, 4, 5, I don't know, 3, 10, sort of something like that, if you have 10 nodes. So x is like this, this, and then my statistic is like this. So this is all I that are in V, and xij's that are in the edge set. And so if I write the density with respect to the counting measure, this part is similar to what we had in the Gaussian case. And then there's going to be some log partition function. This model is called the Ising model. And it's a model used in the statistical mechanics, for example, to model the ferromagnetic sort of phenomena. So this is like the spin of some location, either an atom or something else. I don't recall the exact, but it's like a state of the whatever is at point position I. So the spin of that guy, and it's either -1 or +1. So this is a distribution on the entire state of the material. So in the like equilibrium, some of them would be +1, some of them would be -1, and it would be random. But this gives you the probability of observing a set of these plus and -1s. And for example, if the theta ij's are very positive, all of them, it could be like, usually the E is like a lattice. So it's just, the graph is like every point is connected to these, let's say 4 points, except at the boundary, or like a three-dimensional lattice. And so if these theta ij's are positive, then it means that if I have a majority of my neighbors have a certain spin, then this is going to be large if I have the same spin as well. So then the probability that the state would go higher, be higher. So it's more likely that I have the same spin as my neighbors. If the theta ij is negative, then it's more likely to have the opposite. So if the majority of my, so basically you would try to counter or be like your spin would be the opposite of your neighboring. You would like to have it to be negative because that would increase the probability. So then the overall sort of interactions of these defines a probability distribution. And there is like one state that has the most probability or most probable state. That would be like, what do you like to know, for example? And there are interesting phenomena that happen. So there's like usually a parameter temperature here that controls everything. And depending on the temperature, sometimes there's like some phase transition. So you'd say that like you see the distribution basically like puts almost all the mass on a certain state. Or if you change the temperature, that state flips. All of them are all like have the same spin, or at some like transition they could have very complicated behavior, and then the opposite case would be another sort of stable setup. In any case, this is the Ising model. It's just another exponential family, and this log partition function is not easy to calculate. In this case, it's just going to be a summation. So you have to sum over all these possible 2 to the n choices. So it'll be log of that summation, basically. That makes the inference much more challenging relative to this, for which you have a closed form solution. Questions, comments? Okay, so one more example. So you could have a more abstract space. Suppose I have an abstract space of graphs and end nodes, and then I can define functionals or functions on the space of graphs. So my T of G would have these statistics: T1G, T2G, dot dot dot, TNG. And these could be like different statistics, various statistics on the graph. You could define other functions. Any function that maps the graph to a real number would do. Usually people take these things like the number of edges, number of triangles, number of R stars, things that look like this. Triangles are things that look like this. Edge is clear. So how many edges you have, how many triangles, closed triangles, how many open triangles, let's say how many stars, and you can have like a bunch of these, and then you form your statistic, and then the natural, and then okay, so the space is this, and then the measure is like counting measure again. Your undiscrete spaces usually have counting measure. Counting measure assigns like the size of the set to each set. And so the natural exponential family would look like this. And this defines the distribution of graphs, which is interesting. So it's an abstract sort of distribution, but it's a discrete distribution. So some graphs are more probable than the others, depending on these parameters. And so you can define distributions on more exotic objects, not necessarily like numbers. So if you have some combinatorial structure, like a space of graphs, you can still put a probability distribution, like a family of probability distributions. And you can try to infer these parameters if you have a sample of graphs from this model. So these things are called exponential random graph models, and they're used in practice. They're very popular. And there are sort of issues in terms of what kind of distributions you get. There's some degeneracy issues. Sometimes, again, like the phase transition behavior here, it could be that for certain parameters, the distribution so puts all the mass on like complete graphs or like empty graphs. And so there has been some, or a lot of works in trying to fix that. But in any case, you would get distributions like this. The idea is that you can define interesting distributions, like families of distributions, beyond, let's say, usual elementary probability distributions that you have learned in like probability 101. And then it allows you to sort of do statistics, basically. Okay. Questions, comments? Should we underline measure, something like that? Okay, no questions? Okay, so suppose these are quite straightforward then. So the next result is that in a full rank canonical exponential family, so we're going to assume most often from now on that we're working with full rank canonical exponential families. I'm going to use this abbreviation FRC, full rank canonical exponential family. The first result, maybe the second result, is that A is convex, is a convex function on the domain. Its domain is just domain of a convex function. I think we have seen this before. It's just a set of all theta for which A theta is finite. So this is an example where A is, in general, you can think of it as a function from Rd to the extended real line, R union infinity. For some values of theta, the integral will be infinite. So those are not the interesting cases, but this is, as I mentioned, I think in discussing convex functions, in convex analysis, usually you work with extended real valued function, or like, extended real valued functions. And so the point here is that this as such function is convex. And a follow-up to that is that the domain of any such function would be a convex set. So this follows because the domain of any convex function is a convex set. So to prove the convexity of this, you would use this as an integral formula, if you recall, and then you use the Holder's inequality. So I've set it as an exercise. I don't recall if you will see it in your homework problem. You may or may not, but the proof, like the outline of the proof is given here. So you can write down the Holder's inequality and basically prove that this is convex. I'm not going to go into the details, but this is one of the interesting results about the exponential families. So exponential families give you a source of interesting convex functions. So for example, this guy, which is a multivariate function, is jointly convex in both of the parameters. And this may not be immediately obvious to some people. So it's an interesting sort of fact, and it gives you examples of convex functions. Questions about this? Okay, the second point is that in a full rank exponential family, so we're going to talk about the properties of A basically. A has a lot of properties. One is that it's convex, hence its domain is convex. The next one is that A is actually differentiable and differentiable of all orders. So it's a C infinity function. It's smooth basically. So differentiable of first order, the derivatives continuous, and then second derivative exists and continues and so on. This happens on the interior of omega naught. And moreover, the derivatives are related to the mean and the covariance matrix of the sufficient statistic. So the first derivative, which is the gradient, gives you the mean of the sufficient statistic. And it's just a function of theta, because the mean is a function of theta. And the second derivative, which is basically the Hessian, is the matrix that would give you the covariance matrix. If you know about the differential characterization of convexity, which you'll probably see in your whole problem as well, if you have a differentiable function, like second order differentiable convex function, then or a second order differentiable function, the convexity is equivalent to the Hessian being positive semi-definite. And you can see from this result, because the Hessian is equal to the covariance matrix of T, and the covariance matrices are in general positive semi-definite, this gives you an alternative proof that A is actually convex, because this side is positive semi-definite. Since cov theta T is positive semi-definite, then the Hessian of A is positive semi-definite for all theta. Hence, A is convex. So this is another proof of convexity once we show this result. So is the statement clear? So if you write this, these things, basically, this is like coordinate-wise statement. So let's try to prove this. So if I differentiate A respect to theta I get the expectation of the I coordinate. The idea here is that we're gonna first compute the moment generating function, and then the derivatives of the moment generating function would be in general the expectations of these guys. So the MGF for a vector valued or a random vector basically is something like that. So you take the e to the, this is the inner product of u, which is a parameter vector. So u is in Rd. Both of these guys are in Rd. And so basically, that's the MGF of T. And we also put a theta here because it also depends on the underlying theta. So if you write this down, we can take the this is basically expectation EUT of x, and I know the density of x, so I can integrate this guy against the density of x, which is this, relative to the underlying measure. And so this part, e to the negative a theta comes out. What I need to compute is the expectation, sorry, this integral, u plus theta t of x, d nu tilde of x. But if you go check what the definition of the log partition function was, basically this is equal to e of a theta plus u. So whatever appears here is just going to be e of a of that guy, u plus theta. So this follows from the definition of the log partition function. So I'll let you verify for yourself that this is going to be the end result. So we have a very nice expression. And if you take the log, basically log the mt would be a u plus theta minus theta. That's why a is called the commulant generating function, because the log of the MGF is called commulant generating function. Okay, so that's the first step. The next part is some sort of a justification, because we want to take the derivative of this. The idea in general is that if I take the derivative of this, I know how to take the derivative of this, but this is also equal to that. If I manage to move the derivative inside the expectation, then good things would happen. So the next part is trying to justify why we can do that. So if theta is in the interior of omega, then you can see that this guy is finite in a neighborhood of 0. The reason is that because this is in the interior, I can take u, the del2 norm, to be less than epsilon for sufficiently small epsilon, so that this whole thing is in the interior again. So that's the definition of the interior. So theta is in the interior. I can pick u, the length of u is small enough. That's the ball basically. The radius of the ball that's inside the interior, so that u plus theta is in the interior. So this means that basically this function, as a function of u, is finite in a neighborhood of 0. Basically, this is what it means. Okay, so in a neighborhood of 0, basically is a neighborhood of theta in terms of this shifted version. So because theta is in the interior, this is finite in the neighborhood of 0, and then this is a result from probability that he can prove that dct implies that mt is differentiable in the neighborhood of 0. And then we can change the order of differentiation integration, and then we can repeat this basically anytime you want, and you get that it's C infinity in the neighborhood of 0. So this is dominated convergence theorem. Dominated convergence, which is basically the building block of these interchange of expectation and differentiation, or limits and expectations, basically. So differentiation is a form of limit. So if I want to change the limit and expectation, I can use the DCT to do that. And this is enough. So I'm not going to prove this, but you can try to verify that. At least show that it's differentiable once, and I can compute the derivative of this by moving the differentiation inside the expectation. Okay, so that's the formula we had. So we're going to take the derivative. So if I take the derivative of this side, what do I get? I'm going to take the derivative with respect to u. So this would give me, what do I get if I take the derivative of this with respect to u? Anyone? derivative with respect to u, with respect to ui, let's say. What would it be? Right, so I have to take the derivative of this, will be partial. This part is constant, so we get partial with respect to u, a u plus theta, and then times the entire thing. Okay. Right, I'm going to write it. The entire thing would be just m of tu, the thing itself. So that's this guy. Okay, so that's the derivative of that side. For this side, if I take the derivative, as we argued, we can move it inside, so I get expectation of theta derivative with respect to ui e ut. So what is the derivative of this guy? This is just, let's say, summation j from 1 to d uj tj. Yeah, so if I take the derivative, this would be ui. So I get, sorry, the derivative would be ti, right? Yeah. I have to take the ith term, derivative of items, and then you get this. Okay, so that's this guy that we have here. So that's this, and the other side is that. So these are just coming out by taking the derivatives, these two terms. Then I set u to be 0. This holds for any u. It's valid in a neighborhood of 0, in particular at 0. So we set u to be 0. This is going to be 1. And this is also going to be 1. This is going to be 0. You can see that if I take u to be 0, then the MGF is 1. That's true always. So I get the result. I get that partial of A with respect to ui evaluated at u is expectation of, evaluated at theta. Is expectation with respect to theta of ti. And you can just call this partial with respect to theta I, because ui is just a dummy variable. This just says that partial with respect to the ith coordinate. So you can call it whatever you want. You're evaluating theta, but that's the ith partial derivative. This is sort of the same as that. So that's what we wanted to show. The covariance, I'll leave it as an exercise to you. It's just you have to take the second derivative. And we did it once, you do it twice, and covariance comes out. Sounds good? Are you using T expectation? No, I'm just, at this point, I'm just plugging in u equal to 0. If I plug u equal to 0, plug in u equal to 0, this evaluates to 0, to 1, right? Okay, yeah. Yeah, this is not going to separate into this times that. No, just evaluate. Okay, any other questions? Yeah, so the idea is simple. This is a general idea about computing the moments by computing the MGF. But the fact is that the MGF here comes very simple, and it's finite due to this regularity assumption in a neighborhood of 0, and then we can take derivative and interchange the derivative and integral, or the expectation. And as I mentioned, this also gives you an alternative proof of convexity. So we have 2 proofs. Questions? So this gives you an easy way to compute, fairly easy way to compute expectations in exponential families and covariances. For example, if you have the Gaussian case, I can write the Gaussian theta and 1 as a one-dimensional exponential family, let's say. Here, this is for canonical family. So this is in canonical form. This would be A theta. So the first derivative would be theta, which matches the mean. Here, T of x is just x, right? So we're completing the expectation of x, and then the covariance matrix would be just a variance of x. It's just one-dimensional. So the second derivative is 1, which matches the variance. It's a very easy way of computing. In general, you have to take the integrals. So you know how to take the integrals, but this is much easier. And you can do it for the families that you don't know the expectation. And the other sort of parameter, the covariance matrix. Okay, so we're out of time. Any questions? Just let me point out what I'm going to do next time. And this is going to be a fairly interesting topic, which I'm going to gloss over a little bit. The idea is that now that we have this, we can call this a new parameter. So the mean, mu theta. So this is another parameterization of the family, which is like easy to compute, and it's like a smooth. You can see this because gradient of A is going to be a smooth function of the original theta. So if I call this mu a new parameter, this mu is related to theta. And in fact, in the FRC, we'll see, or sort of wave our hands at this parameterization is 1-to-1. You can invert it. So instead of working with theta, this is a nonlinear map, but it's invertible. And so I can go back between the natural parameter and the mean parameter. And the mean parameter is easy to work with because it's easy to estimate. So the mean parameter, if I call it mu, I can always estimate, because it's expectation of T of x, if I have a sample of size n, I can estimate it by the sample mean. Whereas this theta is not so obvious how to estimate. You can do MLE, but this is more natural to estimate. So you can estimate this and then invert the using the inversion transformation, like the inverse of the gradient of a mapping, to get back the estimate of the natural parameter. And that turns out to be actually the MLE, as we'll see. So we'll work with this. And then there's some sort of interesting properties about these mean parameters. The idea of that I'm going to try to express in this slide later is that basically any set of mean parameters that you can realize with a continuous density can be realized by an exponential family. And in fact, can be realized in the most random fashion. That's the maximum entropy principle. So exponential families are sort of have some optimality. So they're sort of, they can give you any possible mean parameterization or mean parameters that you want, or you can achieve with any possible density, and then they achieve it with maximum randomness, basically, subject to those constraints. These are the things I'm going to talk a little bit about next time, and then we wrap up our discussion of exponential families. Questions, comments? You can take a look at these slides. There's some heavy math. I'm going to probably gloss over this. So there is a theorem. This is a very interesting theorem, but proving it requires a lot of math. But I'll talk a little bit about this. You can take a look at the proof if you're interested. And then we'll be done with exponential families. Okay, questions, comments? Okay, let's stop here. Thank you, guys.